This is Chemistry Unit 12, Gases. Now we'll look at the gas laws. Now usually gas laws are solved in liters for volume and Kelvin for temperature. So keep that in mind. The first law we'll look at is Boyle's law. So the Boyle in question is Robert Boyle, who you see in this image. He was an Irish scientist, and he performed experiments that looked at the relationship between the pressure of a gas that is trapped and its volume, temperature, and the amount of a gas, which we're going to call N instead of M, and you'll learn why later. These were constant. So why I'm mentioning these variables to you, well, if temperature and the amount of gas are constant, then T and N will not be involved in Boyle's law, and they're not. So we're going to focus on P for pressure and V for volume. Now this website I'm going to show you in real time because it'll help you understand what his law says. But you're free to check it out. I will post that for you. And if you'd like to learn a little bit more about Mr. Boyle, I will post this website as well. So let's check out his data first, and then I'll show you the website. So here are some of his experiments. So he looked at the pressure of mercury and the volume of mercury. So what did he do to the pressure? So if you look at the pressure, right, what's happening to each of these numbers? They're going up and up and up. What's happening to the volume? It's going down and down and down, right? So what do you notice about those results? What kind of relationship is this when one variable goes up and the other variable goes down? This is what we call an indirect relationship. As the pressure increases, the volume decreases. And it would be the reverse in the opposite direction. Decrease the pressure, and you increase the volume. So here's that website, right? So first of all, this is a great graph that shows you what an indirect relationship looks like, right? P goes up, and the volume is going down. Now also take a look at the actual experiment. See how mass is not moving, temperature is not moving, the pressure gauge is going up, right? You can see it increasing. And what's happening to the volume? So as the P goes up, right here, this is coming down. So watch, down. So P goes up, V goes down. And then you can see when it reverses itself, the volume goes back up. Now Boyle used mercury, but every gas could possibly be measured, right? But what he also looked at is this third column. So what he did is he took the P and the V for each experiment and he multiplied them. So this last column is showing the results when he multiplied P times V. So what do you notice about these numbers? Doesn't matter what experiment it is, look at those numbers. But every gas will have different values for P times V, but just like mercury, they will remain constant under different measures of P and V. So there were no temperature changes and the amount of gas was the same. So mathematically, P times V is what we call constant. So yes, I know that pressure goes up and volume goes down, but if you multiply the P and the V, no matter what experiment you have, it's going to remain constant. So here's how the law developed. If you just take the first two experiments, you could compare any two experiments, and you multiply the P and the V, you're going to get a constant value. So you can use this under different situations, right? You can take any two experiments and compare them. And that's what Boyle's law is. It's P1, V1 equals P2, V2. So let's take a look at what this actually means. Let's try an example here. So what happens to the volume of a helium balloon if it is let go at a volume of 20.0 liters and a pressure of 1.00 atm? It ascends to a height that drops the pressure to 0.1 atm. Okay, so what does all this mean? Okay, so you have a balloon, right? You have a helium balloon, and you let it go, and something's going to happen. So what you need to understand is, what do you know about the balloon to begin with? And then do you know anything else once you've changed the conditions of that balloon? You let it go, right? So what's the balloon like to begin with? Well, it's got a volume of 20.0 liters and a pressure of 1.00 atm. That's your initial condition. That's your P1 and V1. And then what happened? It was let go. So when that balloon rises, what happens to pressure? Pressure drops, right? Because that's well above sea level, so there's less air up there, so there's less pressure. Now the question is, what happens to the volume? So obviously if you just follow his law, the volume should increase. But what would it actually be mathematically? How would you solve this law? Well, let's start with what we have. You have the 1.00 atm, that's standard pressure, and you have a volume of 20.0 liters. You let the balloon go, the pressure changes to 0.1 atm. So the first thing to do, and I don't need to see all of these steps, in fact, just how you plug it in and solve it will be enough, but since this is notes, I like to explain as much as I can. So what did I do over here? I just multiplied these two, and I did keep my significant figures the same. There's 3 in each, so 20.0 atm liter. I just didn't eliminate any units. And then over here, I just eliminated the parentheses. Now the question is, how do we get V2 by itself? Well, 0.1 atm is actually being multiplied by V2, so to move it to the other side, you will have to divide, right? So then you take 20.0 atm divided by 0.1, atm liter, and then divide it by 0.1 atm. So your atms will cancel out, and you will be left with liters. Okay, now if you divide this in your calculator, 20.0 divided by 0.1, your answer is 200 liters. So that does make sense according to the law, right? That volume increased. And then did you write your result in correct significant figures? Yes. 20.0 has 3 significant figures, 0.1 only has 1.